Assalamu alaikum everyone, and today we are going to solve miracle number 2. So in this miracle, this is our problem number 2. In problem number 2, we have given overall pressure ratio, we have given mass flow rate, we have given maximum temperature. This means the temperature before the after the combustion chamber. We have given PA, we have given that is 1.01 bar, P2 that is 4.04 bar. What is P1 and P2? P1 and P2 are actually here. This is our compressor. This is air inlet. The inlet pressure is P1 and the outlet of the compressor pressure is P2. Mass flow rate is 60 kg per second. Maximum temperature is 650 degrees centigrade and is equal to 923 Kelvin. PA is equal to PI is equal to 1.01 bar and P2 is also given. TA is given, TI is given, and we have given NC is equal to 0.8. We have given NHPT and we have given NLPT. That is the isentropic efficiency of combustion, isentropic efficiency of high pressure turbine and low pressure turbine isentropic efficiency. And we have also given shaft mechanical efficiency. Now, what is shaft mechanical efficiency? The shaft mechanical efficiency is actually, you may see that here is our shaft that is coupled with high pressure turbine to the compressor. So this shaft has certain mechanical efficiency to transmit the power output from this high pressure turbine, and if the complete power is transmitted to the compressor, then it means that it is 100% efficient. But in this case, due to friction and some other losses, this efficiency is 0.98. So I will read this question and I will show you this figure so that you must understand this figure and how it has been done. In a marine gas unit, a high pressure stage turbine drives the compressor. You should know that in this question we have two turbines. One is high pressure turbine and one is low pressure turbine. The high pressure turbine drives a compressor, and a low stage turbine drives a propeller through a suitable gearing, and low pressure turbines drive a propeller. And here I have written generator, I mean the writer of this assignment. So here it is not generator, it is actually propeller. Here it is propeller. Through a suitable gearing, the overall pressure ratio is given, and the conditions are 1.01 bar and 25 degrees centigrade at the inlet. Maximum temperature, I mean the temperature after the combustion chamber. This is our point 1 where temperature is where the temperature is 25 degrees centigrade and the pressure is 1.01 bar. 1.01 bar is our pressure, and this point number 3, this point is actually the output of compressor, output of combustion chamber, and at this point we have our maximum temperature, that is 650 degrees centigrade, that is also given to us, and we have also given the efficiencies of low pressure turbine, high pressure turbine, and mechanical efficiency. So these are all the things that has been given to us. Now let's look at its TS diagram. So this is TS diagram. Process 1 to 2, I should zoom it out. Process 1 to 2 is what? It is actually compression process. Process 2 to 3 is what? It is actually combustion process. This is what? Compression process. This is combustion process. What is process 3 to 4? Process 3 to 4 is actually expansion in high pressure turbine. Expansion in high pressure turbine. 4 to 5 is what? Expansion. It is also an expansion, but it is in low pressure turbine. This is high pressure and this is low pressure turbine. So these are the some basic and fundamental things that we should know. Now it comes and that how to solve this numerical. It is actually very easy. Only it is just like the previous one, but a few steps has been added. I will go a bit faster on it, and I will focus on the new concept. So first of all, we do not know the T2. I will again draw it here. This one, then this one, and from here to here and here to here. 1, 2, 3, 4, 5, and again. We do not know this T2. So as T2s, not T2 and not T2s. So we will first calculate T2s. Then the process is simple. It is actually P2 by P1 into gamma minus 1 over gamma. I have already covered it in the video number 1. I mean the problem number 1. So T2s is can be easily get from this relation. The isentropic efficiency is also same, that is from the formula T2s minus T1 into T2 minus T1. So we will get what? T2. First I find T2s and then I found T2. T2s is T2s by T1 into P2 by P1 into gamma minus 1 over gamma. So we find the T2. Now work input to the compressor. Now here is the point. It is very good point. Work input to the compressor is equal to work output from the high pressure turbine. This is a very important statement. The work that is input to the compressor is equal to work output from the high pressure turbine in ideal case. In ideal case, but we have certain minimum losses, that is actually it is not 100%. Our this transmission of work from high pressure to the compressor is not 100%, it is actually 98%. So we will multiply 0.98 here with the work output from high pressure turbine. Work output from high pressure turbine is like this one. This is process 1 to 2, this is 2 to 3 combustion, and 3 to 4. This process 3 to 4 is here, process 3 to 4. And I will multiply 0.98 with it to equalize it to get the work input to the compressor. So it is equal to T3 minus T4, that is equal to 161.42, and T4 is equal to 761.57 Kelvin. So simple. So what is the benefit of it? I will get the direct T4 point temperature from it. Actually there is no other way to get this temperature if we do not use this relation, it would become too difficult to find this temperature by other relations. So NT for high pressure turbine is equal to T3 minus T4, T3 minus T4s is equal to 0.83. Fine, is equal to 0.83. So 923 minus T4s is equal to 194.49. T4s is equal to 728.51 Kelvin. T4h is equal to 728.51 Kelvin. So it is very good. We have find our T4s. Now we have reached this point. We know we know all the parameters of point 1, point 2. We know the parameters of point 4, but we do not know the parameters. But we do not know the parameters of point 3. I mean the temperature 3. But fortunately, it is given in the question. Now we know T4s by the relation of T3 minus T4, T3 minus T4s, isentropic efficiency for high pressure turbine. By this relation, I will get temperature Ts and T at this point. Okay, I mean at the output of the high pressure turbine. So now our problem is that we want to know the P4. We know that T3 by T4 is equal to P3 by P4. T3 by T4s is equal to P3 by P4. We know P3, yes, the output. We know P3 by P4. No, we do not know P3 by P4 because it is not given to us. But what we know T3 and T4s and gamma minus 1. So this is very good relation. P3 by P4 is equal to T3 by T4s. This relation from for isentropic process pressure and temperature relation from thermodynamic 1 gamma into gamma minus 1 here. So P3 by P4 is equal to T3 by T4s into gamma divided by gamma minus 1 is equal to 923. We will just plug in the values. 923 by 728.51 to the power 1.33 divided by 0.33. So P3 by P4 is equal to 2.58 and P4 is given to us. P4 we will find P4 is equal to 1.57 bar. Now since P5 is equal to P1 and P2 is equal to P3, how? I will draw this diagram again and again. This is 1, this is 2, this is 3 to 4 and this is 4 to 5 and it goes here. So this is 1, 2, 3, 4, 5. So this pressure 3 is equal to pressure 2. This pressure 5 is equal to pressure 1. Okay. Now why we have written it here? Actually we will calculate a very beneficial thing from here, that is P5 is equal to P1 and P2 is equal to P3. We will calculate what? We will calculate from here P4 by P5. How we will calculate? We know that P4 by P5 is equal to P4 by P3 into P2 by P1. How? Now this is actually written P3 is equal to, this is P3 and this is P2. P3 and P2 are equal. P3 and P2 are equal. So this P2 will be cancelled with this P3. Okay. And P4 and P1. What is now what is P4? What is P4 that we have already found? That is 1.57 bar. We have already found it. That is 1.57 bar. So just plug the value of P4 and plug the value of P1. For P5 we will use the value of P1 because P5 and P1 are on the same pressure line, so its pressure is equal, and the pressure this pressure we have found already. We know that this pressure is equal to uh, some value that we know already, P3. So here this is the basic trick that we used here in order to find the value of P4. So T4 by T5 S is equal to P4 by P5 into gamma minus 1 over gamma. So now we will use this relation and we will find the value of T5S. We will find the value of T5S. Now this T5S is equal to 686.09 Kelvin minus 3. We will just plug in the value of P4, P5, T4. We will get the value of T5S. And from the value of T5S, I will use the relation of isentropic efficiency of low pressure turbine to get the value of T4 minus T5, and to get the value of T4 minus T5. So I will use this T4 minus T5 value to get the work output from low pressure turbine, and heat supply is actually process 322, that is combustion process, that is here. We will just as like the previous video, as we found the value, we will also find the value of heat supplied, I mean the heat supplied by the combustion process, and work input from low pressure turbine, that is 6.70 kilojoule per kg. So work output and heat supplied. Now it comes the cycle efficiency. Cycle efficiency is equal to net work output divided by heat supplied is equal to 0.149. Cycle efficiency is equal to 15%. So we found it. Net work output is work output, net work output and heat supplied. Heat supplied is this one, and net work output is actually the work output from low pressure turbine. Now why it is the net work output? As we know that if I draw here, that here we have high pressure turbine. This high pressure turbine is coupled with compressor, and at the output of high pressure turbine we have low pressure turbine, and this low pressure turbine is actually giving us the net work. So by just putting the values, cycle efficiency is equal to net work output by heat supplied, and we get the value of cycle efficiency. Now shaft power is equal to m dot cpt4 minus t5s, and shaft power is equal to 4551 kilowatt.